At the start of the semester, we were talking about standing waves and standing waves with boundary conditions, both either both ends the same or one fixed and one loose. And I could always remember the equations from it, but in class people would always talk about, well, to get the equations, well, we know that for one with different boundaries, it's odd number of quarter wavelengths. So then this is the equation. Whereas I'd always figured that out the other way around, and I couldn't figure out how you'd know it was the number of half wavelengths or quarter wavelengths for each without memorizing the equation. But then I decided to actually think about it. So instead of just look at the equation. So if we draw something, if we do the one where both ends are fixed, and let's just try to draw it at the lowest possible number of nodes. So for both fixed, well, you'd assume then if they're both ends are fixed, then both are going to be the same, and that it's going to be symmetric. So either both ends are going to be at, where if we were considering this is just a sine or cosine, a sinusoidal wave, both ends are going to be at the zero, or at the max, or at the min. So that gives us three options, and just assuming the symmetry. So if they're both at the max, we're going to get a wave pattern for a maximum wave that looks like that. If they're both at the minimum, we're going to get one that looks like that. And if they're both at the middle, then we're going to get something that looks like that. Now, if you think about when you hold a string and fixed above ends and flick it, it doesn't go flat for a bit and then drop down. It looks much more like this. And we can see that's even more obviously how it's going to be if we draw the next stage upwards of the next frequency of it by doing, if it's both at the same, and we're hitting the zeros, then we're going to get that as equivalent to this. But if we do these, where we're hitting the top, we're going to get top and then that's inverse. No string ever looks like that. So therefore we can assume that we're going to be hitting the ends of the string when we hit the center. Like that. Looking at that, we can see that from the second stage to the first stage to the second stage, we've added a half wavelength. And it's going to keep on doing that the more oscillations we fit in the same period. So therefore, we can see, just from looking at the picture, that the length has to equal n, where n is any positive, any number greater than 1, half wavelengths. And we can actually see that from looking at the picture, and that's how you get it. And then from there, it's simple to turn it into the form we're familiar with. Because then this turns into lambda equals 2L over N. V equals frequency wavelength. So therefore, the frequency equals V over lambda equals V over 2L times N, where is an integer greater than equal to 1. So that's how you get that from doing the drawing, and it makes so much more sense as to why that's the answer. Now let's see if we can do the same thing with the one bound and one fixed. Well, we know that the bounds are going to be at, if we consider it on an axis, at the 0. So what's the loose end going to do? Well, we're waving around like this. Is it going to end here and just be hovering at an exact middle in midair? That doesn't seem very likely, does it? Or are we going to end at the top, or alternately, if we're curving the other way, the bottom? That looks a lot more like what you'd expect when you flick a string. The end shoots up. It doesn't just stay level with your hand. So, therefore, we can see that we're going to always have this weird quarter wavelength sticking out because our lowest state is now going to be that, going from that to the maximum. So, but our second lowest state, we still have to have that flick at the end. So we're going to be that. So therefore, this is 3/4 wavelengths. So we're going to get the odd number of quarter wavelengths that we're familiar with. So we can then write that L has to equal n quarter wavelengths, where n is greater than 1, n equals, I didn't write that properly, 1, 3, 5, da da da. And then we can do the same thing to convert it into the equation form that we're familiar with, by getting this time that lambda equals 4L over n, plugging it in to this one, we get the frequency equals 4 equals, velocity, n velocity over 4L. This is an n. This is a very bad n. And then where n is an odd integer. And that's the equation we're familiar with. So if you think about it, just in terms of out of all the possibilities, which can you eliminate as nothing you've ever seen a string do before, then you can get from the diagrams to the equations and not just from the equations to the diagrams. Thank you.